one of them may be the one that turns against the other one may be rewarded. So you could set up different numbers in this thing. So if the game is considered from a repeated point of view, this has been studied by Robert Allman and various others, then it is stable for the players to behave in a cooperative way, even though non-cooperative game theory is being applied. Because if the players have reactive strategies so that each side plays with a strategy that as soon as the other side stops cooperating, then the first player will also stop cooperating. So there's a negative reaction strategy tends to enforce cooperation. Now, I wanted to use principles like this for my game theory analysis. And in connection with studying that, I studied the same problem that I really wanted to study on the level of 3 players. I studied it for 2 players. And I did up model games where the players could cooperate, or they could cooperate in various ways. And if the way they would, in a repeated game, they could vary their reactions. So ultimately, I found a formula so that each player would simultaneously have a demand strategy and a utility assignment strategy. There would be a curve. I don't have a picture of it now, but there would be a region of possible cooperation. This was actually had a curved boundary, and each player would say, well, if I am selected to be the agent, then I will select this point on the curve of the maximal profitability. The Pareto, it's actually called the Pareto boundary, the region of possible cooperation. And on the other hand, I'm going to demand this much of a level of profit. So if the other player doesn't give me that much, then I will not, next time I will stop accepting him. Well, this is ultimately designed to work on a continuous basis, and I could show you some of the mathematics of that. But I just wanted to mention that in the time before I had gotten to the 3-player models, I worked on the 2-player, and I went to a meeting, the nonlinear analysis that was organized by someone in Florida. But the first meeting that I went to was in Catania, in Sicily. So I talked about this on the 2-person level there. And later on, there was a similar meeting in the island of Ischia, near Napoli. And I continued talking on this there. I think I may have gotten to the 3-player level there. Don't remember precisely. Now so I could show with the 2-player model, there was a curve of possibilities, and there's let's see, this mathematics, this will be a bit technical. This is how it was done for 2 players. There was a quantity, let's see, that doesn't show, does it? Oh, no. Well, you see there, these are exponential functions, and A1 is something that is a function that's generated, and then this small a1 is generated from the capital A1. And this describes the probability of player 1 accepting that player 2 can be his agent. See, each player can accept the other player as his agent. There's a surrender process by which cooperation is realized. It's like a rotating chairmanship. The agent is like a chairman of in this case, a committee of 2, but later it can be 3. Now, this quantity U1B2 meant utility of player 1 as chosen by player 2, by 2, U1 by 2. And on the other hand, D1, this is something chosen by player 1. This is demand by player 1. And then the quantity capital A1 is a function of that, and this function is also modified by a quantity that's called E1, which really is epsilon 1. And that was to be small. And what happens is we ultimately let that become smaller and smaller. We're concerned with the limiting behavior. And so this exponential function means that if U1, B2 is bigger than D1, and E1 is sort of small, then this quotient will be quite large. This exponential will be even larger. Until finally, the number A1 will be nearly 1, which means that player 1 would have a very almost certain probability of accepting player 2 as his agent. And that the thing is completely dual for player 2. Now, this number here was chosen by player 1, U2, B1, but then player 2 reacts to it through the medium of his demand, which is D2. And this produces a reactive situation in terms of 2 players. And it was found that there was an equilibrium, and there's some more to say about the rules. But what happened was that if the quantities E1 and E2 would be made small, it was found that they need to be the same quantity, which is a technical thing. I later called that E3, or epsilon 3. But then the equilibrium would have much more greater and greater efficiency if the epsilon quantity E1 or E2 would be smaller, and this means that the players would be very sharply reacting. Player 1 is reacting to U1, B2. He's reacting to what player 2 chooses. That really is the point. There's a bargaining curve, the Pareto boundary of the accessible region of cooperative game arrangements that and player 1 reacts to what player 2 would give him when he does surrender to player 2, that he does accept player 2 as his agent. Now I have some charts that show how this works out when it's generalized to 3 players. How am I going to get? Oh, I have to go back. Now this isn't, well, this is more, see, E1 and E2 there become E3, and that's epsilon 3. Now this is 3 players, but I should maybe look at a previous one. Let's see. Radiographic A. Yes, this is a nice